right now, like literally right this second, running through your veins, your immune system is actively manufacturing this highly potent chemical weapon.
It really is. It's fascinating.
Yeah, I mean, for all intents and purposes, it is microscopic bleach. When your white blood cells detect an invading bacteria, they just deploy this chemical to literally dismantle the pathogen from the inside out.
Right, right.
But then you look out into the world, and this exact same chemical is pumped into, like, commercial food processing plants to scrub down heavy machinery. And you can also just go to the store and buy it in a spray bottle to soothe the sunburn.
Which sounds completely impossible.
Exactly. Welcome to the deep dive. We've custom-tailored this exploration just for you. Today, we are unpacking an incredibly detailed article from Era Organics. It was written by Nikki Chase and published back on June 8th, 2026.
It's a great piece.
It really is. The subject is a chemical compound called hypochlorous acid. And our mission today is basically to understand a profound paradox. We need to figure out how a single chemical can be ruthless enough to sanitize raw sewage, yet gentle enough to be synthesized on demand inside your own bloodstream.
Yeah, it is a profound duality. I mean, and to really understand it, we have to look at this as just an absolute masterclass in chemical balance and reactivity.
Right.
Because, most of the time when we think of heavy-duty sanitation, our minds just automatically go to harsh synthetic chemicals, the kind that smell terrible, right, and require all those giant warning labels.
Oh, yeah, skull and crossbones stuff.
Exactly. But this molecule, it represents how nature solved a biological problem that human industry has honestly spent centuries trying to replicate at scale.
Okay, so before we can understand how it, cleans water or heals a diabetic skin ulcer, we really have to look at the blueprint.
Right, the actual structure.
Yeah, we have to look at how this molecule is built.
Yeah.
Because even the way scientists write its name is a subject of intense debate, which I find hilarious.
Oh, it causes so many arguments.
I bet. So the compound is incredibly simple. It consists of just 3 atoms. You've got hydrogen, oxygen, and chlorine. But looking through the scientific literature, it is written in 2 entirely different ways.
Yeah, it is.
Sometimes you see it as HClO and other times as HOCl. And the difference isn't just a typo, right? Like HClO is the empirical formula. It's just a list of the ingredients.
Right, exactly.
But HOCl is the structural formula. So the way I wrap my head around this, calling it HClO, is like throwing flour, sugar, and eggs on a table.
Great analogy.
Right. But HOCl is the actual recipe showing how those ingredients connect to make a cake. It shows the physical bonding sequence. The hydrogen connects to the oxygen, and the oxygen connects to the chlorine.
And that structural sequence that dictates literally everything about how the molecule behaves in the real world.
Oh, wow. Everything.
Everything. So, the International Union of Pure and Applied Chemistry, or IUPAC, officially names it hypochlorous acid.
Okay.
The prefix hypo, that indicates that the chlorine atom is in its lowest possible oxidation state.
Right.
And that specific arrangement, the hydrogen bound directly to the oxygen, it gives the molecule its distinctive chemical properties.
Okay.
Now, in chemistry, hypochlorous acid is technically classified as a weak acid, possessing a pKa value near 7.5.
Okay, wait. Let's unpack that classification for a second.
Sure.
Because I have to push back on the terminology here. If this is a quote-unquote weak acid, meaning it like barely fully dissolves or dissociates when you drop it in water.
Yeah, exactly.
How is it such a ruthless killer of bacteria? Because when I hear the phrase acid that destroys organic matter, my brain immediately goes to something like hydrochloric acid.
Oh, sure. The scary stuff.
Yeah, a strong acid that aggressively melts things on contact. How does a structurally weak acid do this kind of catastrophic cellular damage?
Well, so the paradox of hypochlorous acid is that its weakness as an acid is actually the precise mechanism that allows its incredible strength as an oxidizing agent.
Wait, really?
Yeah. In chemistry, a weak acid is basically just one that doesn't completely let go of its hydrogen ions when it's submerged in water.
Okay, I'm with you.
So strong acids like the hydrochloric acid you just mentioned, they completely break apart. They just send hydrogen ions flying everywhere.
Oh, wow.
And that massively lowers the pH of the environment, which is what causes that aggressive melting or, that burning effect on human skin.
Oh, so that's the burn.
Exactly. But hypochlorous acid doesn't do that at all. It mostly just stays perfectly intact as a whole, electrically neutral molecule.
And that neutrality is like the stealth mechanism.
It operates entirely on stealth. Because the HOCl molecule has absolutely no electrical charge, it doesn't trigger any alarm bells when it encounters a single-celled organism.
It just sneaks right up.
It effortlessly slips right through the protective cell walls of bacteria. But once it actually gets inside the cell, that's when its oxidizing power activates.
Right.
And oxidation essentially just means stealing electrons. The HOCl molecule aggressively rips electrons away from the pathogen's vital proteins and its DNA.
I mean, stealing an electron doesn't sound inherently violent to me.
Oh, yeah.
But from a microscopic perspective, it's structurally devastating, right?
Completely.
Like when you rip an electron away from a protein, that protein physically unfolds, it denatures, the bacteria's internal machinery just collapses.
Yeah, the pathogen is effectively destroyed from the inside out rather than being melted from the outside in.
Wow.
And this stealthy, internal destruction is what allows hypochlorous acid to eradicate pathogens without causing all that collateral acidic damage that would melt the surrounding environment.
That is wild. And that structural stealth is honestly the perfect segue to comparing it with the heavy hitter sitting under almost everyone's kitchen sink right now.
No, ordinary bleach.
Ordinary bleach. The chemical name for traditional bleach is sodium hypochlorite. And if we put hypochlorous acid head-to-head against bleach, it seems like the entire battle basically just comes down to the pH scale.
It really does. The pH scale acts as this critical dial for how chlorine behaves in water. So hypochlorous acid forms, and more importantly, it remains stable in slightly acidic conditions.
Okay.
We are generally looking at a pretty narrow pH window between like 5 and 7.
Gotcha.
Bleach, on the other hand, operates on the complete opposite end of the spectrum. It is highly alkaline. It's usually manufactured and stored at a pH between like 11 and 13.
Which is really high.
Oh, the extreme.
Yeah.
And that extreme alkalinity is the actual source of bleach's toxicity. It causes chemical burns on contact. It severely irritates your respiratory system if you inhale the fumes.
Oh, yeah, we've all smelled that.
Right. And it requires massively high concentrations to actually kill pathogens effectively compared to HOCl.
Yeah.
Furthermore, when that highly alkaline bleach reacts with organic matter out in the environment, it forms these harmful chlorinated byproducts that just linger in ecosystems.
So bleach basically relies on sheer destructive alkalinity. If hypochlorous acid is like a molecular lockpick, silently sliding through the bacterial cell wall before detonating inside,
Right.
bleach is basically a battering ram that just burns the entire door down.
Yeah, and usually takes out half the neighborhood with it.
Exactly. But the catch with the molecular lockpick is the equilibrium reaction. Because in water, hypochlorous acid is constantly fluctuating back and forth on this sort of chemical seesaw.
Right, it's very delicate.
It shifts between being intact HOCl and breaking apart into free hydrogen ions and hypochlorite ions. And if you think about managing a swimming pool in the summer, you are literally managing this exact seesaw.
That's a perfect example.
Because if the pool water gets too alkaline, drifting above a pH of roughly 7.5, the HOCl molecule fractures. And you are left with just a hypochlorite ion.
And the hypochlorite ion is a dramatically inferior disinfectant.
Why is that?
Well, the reason comes right back to the physics of electrical charge. When the molecule breaks apart, that resulting hypochlorite ion carries a negative charge.
Ah, and the outer lipid bilayer of a bacterial cell wall also carries a naturally negative charge.
Exactly.
So you have a negatively charged ion trying to attack a negatively charged cell wall.
They physically repel each other.
Wow.
It is exactly like trying to force the wrong ends of two magnets together. The chlorine physically cannot touch the bacteria to penetrate the wall, so the chemical completely loses its superpower.
That's crazy.
Yeah, and this is why municipal water operators and pool managers have to obsessively monitor the pH. They're constantly adding minor acids to keep the water in that slightly acidic sweet spot, just ensuring the chlorine stays in that neutral, intact HOCl form. It is a very, very delicate balancing act.
Right. Well, hearing all of this, the logical deduction is pretty stark to me. If hypochlorous acid is non-toxic, it doesn't burn your skin, doesn't create toxic environmental runoff, and actually gets the job done at significantly lower doses because it doesn't repel off the bacteria,
Yeah.
why hasn't it completely replaced bleach? I mean, it seems like traditional bleach is just an incredibly crude tool in comparison.
It is crude, but the persistence of bleach reveals a really fundamental reality of commercial chemistry. Stability is almost always traded for safety.
Oh, interesting.
Yeah, so that extreme alkalinity of bleach, that pH of 13, that is precisely what allows it to just sit inside a plastic jug in an unair-conditioned warehouse for 2 years without losing its chemical potency.
Oh, so it just lasts forever.
Exactly. It provides brute force cleaning power with incredible long-term industrial stability. Hypochlorous acid, on the other hand, is precise and safe, but it is deeply fragile.
Right.
So the very properties that make bleach biologically dangerous are the exact properties that make it a viable, highly profitable commercial product.
Okay, so since bleach survives the supply chain but causes environmental collateral damage, and hypochlorous acid is perfectly safe but highly fragile, the industry has to figure out how to, like, bypass the warehouse entirely.
Yes.
You can't just buy a jug of it that lasts a decade. You have to literally manufacture it on demand. So how are engineers actually conjuring this chemical into existence at scale?
Well, there are a few primary pathways. The most rudimentary method is just a direct reaction. You're introducing pure chlorine gas directly into water,
Right.
and the gas reacts to form hypochlorous acid alongside hydrochloric acid. Another method is an industrial conversion process.
Okay, how does that work?
You take that highly stable, highly alkaline sodium hypochlorite, so traditional bleach, and you intentionally react it with an acid. By forcefully driving the pH down, you force the chemical to yield hypochlorous acid and sodium chloride, which is really just salt.
Okay, but the third method detailed in the Era Organics article is electrolysis. And this one blew my mind.
Oh, it's fascinating.
You literally take brine, which is just sodium chloride dissolved in water, and you pass an electrical current through it using, like, titanium or graphite electrodes. It honestly sounds like a high school science fair volcano.
It does.
You're just shooting electricity into a jar of salt water to get a medical-grade disinfectant.
The starting ingredients are incredibly simple: salt, water, electricity. But the actual electrochemical execution is really volatile.
Oh, is it?
Yeah, because when you pass that direct current through the brine, those titanium electrodes are physically stripping electrons away from the dissolved chloride ions.
Okay.
This oxidation at the anode generates pure chlorine gas directly in the water. And then that newly formed gas instantly reacts with the surrounding water molecules
Right.
to produce hypochlorous acid,
But wait, you're fundamentally generating pure chlorine gas in the middle of this process.
which is incredibly dangerous.
Yeah.
The process demands immense ventilation, hyperspecific temperature controls, and highly precise automated pH management. If the voltage fluctuates even slightly or the temperature rises too high, the equilibrium shifts immediately.
And then what happens?
You start generating extremely toxic, unwanted chlorinated gases.
Oh, wow.
So the precision required to capture hypochlorous acid in its active neutral state without, accidentally filling a factory floor with pure chlorine gas. It is a true marvel of modern electrochemical engineering.
Okay, but once engineers pull off that high wire act and actually capture this molecule, the applications are endless.
Right,
Like,
completely endless.
because that lockpick mechanism we talked about, sliding past a cell wall and oxidizing the interior, it relies on basic cellular physics, so it scales universally. It basically works on almost anything single-celled.
Exactly.
And that is why this chemical pops up in industries you would never, ever associate with one another.
Versatility is truly staggering. Like in healthcare and dermatology, it has completely revolutionized wound care. Yeah. Traditional antiseptics like hydrogen peroxide or iodine, they work, but they are totally indiscriminate.
Right, they burn.
They foam up and they sting terribly.
Yeah.
Because they are actively oxidizing and destroying your healthy human tissue right alongside the bacteria.
Ouch.
Right. But hypochlorous acid cleanses diabetic ulcers, burns, and abrasions without harming the surrounding healthy cells at all. Dermatologists utilize it constantly for sensitive inflammatory conditions like eczema and psoriasis.
And the reason it doesn't sting, the reason it doesn't melt human skin while simultaneously destroying a single-celled bacteria brings us full circle to the very beginning of this deep dive.
Yes.
We literally evolved alongside this molecule. Because our own white blood cells produce it naturally, our complex human tissues actually have built-in neutralizing enzymes.
We are totally biologically equipped to handle its presence.
Right, and the bacteria just don't have those defenses.
They don't. And that biological compatibility is what allows it to cross over into completely different sectors, like food processing and agriculture. Facilities use it to wash fresh produce, aggressively killing off pathogens like Salmonella and E. coli.
Wow.
And because it is food grade and leaves absolutely no toxic residue behind, it is heavily utilized in organic farming.
You also see it heavily utilized in aquaculture and veterinary medicine, which is amazing. Like, fish farmers pump HOCl directly into the water tanks to treat parasitic and bacterial infections in the fish.
They're brilliant.
It drastically reduces the need to constantly dose the fish with broad-spectrum antibiotics, which is a massive win for preventing antibiotic resistance.
Oh, absolutely.
And veterinarians literally spray it directly onto animal wounds because it sanitizes without causing the animal any pain or irritation.
Yep, it effectively targets the simple biology of the pathogen while completely bypassing the complex biology of the animal or the human being treated.
Right, but, the laws of thermodynamics always demand a toll.
They always do.
If this chemical is a miraculous, eco-friendly, biologically compatible pathogen killer that we can somehow synthesize from table salt and water.
There has to be a catch.
Exactly, there is a catch.
Okay.
The fundamental flaw of hypochlorous acid is its exceptionally short shelf life.
Yeah, the Achilles heel of HOCl is stability. Under the absolute best, most pristine, optimal conditions, it only remains stable and viable for roughly 1 to 3 months.
Just a few months.
That's it.
And maintaining those optimal conditions sounds like a logistical nightmare. The molecule degrades incredibly rapidly if it is exposed to temperatures above 25 degrees Celsius, which is literally just standard room temperature on a warm summer day.
Yeah.
And it is profoundly sensitive to ultraviolet light. Like, the moment direct sunlight hits the liquid, the energy from the light breaks the atomic bonds and it just begins to degrade.
Instantly.
So to keep it viable, you essentially have to store it in a refrigerator, ideally between 4 and 10 degrees Celsius.
Right.
Furthermore, it has to be kept in completely airtight, totally opaque, or specially coated UV-resistant containers.
And don't forget the pH.
Right. If the pH of the solution drifts even a fraction of a point, as we covered, it degrades right back into those magnetically repulsive, far less effective hypochlorite ions.
It is deeply, deeply fragile. And the thermodynamic reality of this molecule forces an ongoing struggle in commercial logistics, because distributing goods globally relies on predictability, right?
Right.
Mass marketing a product that expires in a few weeks mandates an unbroken cold chain and neutralizes itself if exposed to air or light. It's an operational puzzle that most major cleaning conglomerates simply don't want to solve.
Okay, so traditional bleach is basically a Twinkie.
A Twinkie.
Yeah, it will survive the apocalypse, just sitting on a shelf in a hot supermarket warehouse for years without changing.
Right.
But hypochlorous acid is like a delicate, fresh-baked souffle.
Oh, I love that.
It is an absolute masterpiece when it is fresh, but if you just leave it out on the counter in the sun for an hour...
It completely collapses.
Exactly.
That souffle comparison highlights the thermodynamic reality perfectly honestly, because it forces you, as a consumer, to realize a somewhat frustrating truth about the products we use.
What's that?
The chemicals that are the most biologically harmonious, the ones that work elegantly with nature, rather than deploying sheer brute force against it, they're almost always the hardest to commercialize.
Oh, that makes sense.
Right. Nature didn't design the HOCl molecule to sit in a clear plastic spray bottle on a shelf in a grocery store for 3 years. It designed it to be manufactured instantly, used in milliseconds, at the exact site of a cellular infection deep inside the human body.
It truly is a chemical marvel of balance. I mean, we've traced the entire journey of this molecule today, starting as a microscopic weapon deployed by your immune system, scaling up to an industrial sanitizer in massive swimming pools and agricultural fish farms, all the way to a gentle healing spray used by dermatologists.
Incredible.
It is powerful enough to absolutely dismantle the cell walls of E. coli, yet so delicate and precise that it requires an expiration date shorter than a carton of milk.
And harnessing it properly requires just a profound respect for the mechanics of chemistry. The tightrope walk of maintaining the exact optimal pH, the precise temperature, and the rigorous storage conditions just to keep those 3 atoms bound together in the correct sequence. It's a real testament to how complex, seemingly simple chemistry can actually be in practice.
Well, for you listening right now, this completely changes how you interact with the environment around you. The next time you walk past a perfectly maintained swimming pool and catch that incredibly faint, clean scent, or, the next time you apply a high-end soothing wound spray, you will know the exact chemical tightrope being walked right in front of your eyes.
Exactly.
You are witnessing the delicate equilibrium of HOCl in real time.
It kind of strips away the mystery of everyday sanitation, right? And it replaces it with a deep appreciation for the science occurring just beneath the surface.
Absolutely. But I want to leave you with one final thought, something to really mull over long after this deep dive ends.
Okay.
We've spent this entire time marveling at the immense industrial effort required by humans. We talked about the titanium electrodes, the careful manipulation of the pH scale, the refrigeration supply chains, and the UV blocking bottles required just to capture and store this one single chemical for a few weeks.
Right, it's a massive undertaking.
Yet your own white blood cells have been effortlessly manufacturing hypochlorous acid for millions of years. They synthesize it perfectly on demand, without massive ventilation systems to prevent toxic gas, and without the need for an industrial warehouse.
It's wild to think about.
It really is. If our immune system is seamlessly operating as a world-class electrochemical factory for this particular molecular lockpick, what other incredibly potent, perfectly balanced defensive chemicals is the human body producing right this very second that human industry still hasn't figured out how to mass produce?